So we'll pick back up again right here. We are toward the top of page 7 of the Chapter 2 lecture document, the PDF. We just ended with practice problem number 8, and that was really a good stopping point because there's kind of a transition that happens at this point in the lecture as we go into the second half. So what do we have coming up? It's variance and standard deviation. So just kind of say a few words before we look at these and look at their formulas. Variance and standard deviation, we get introduced to them now, but we're not really going to know their full meaning and their full significance until a few chapters later in the course. So we get introduced to these and we calculate of some variance and standard deviations of data sets by hand, and that's going to be really good for us to see now. Just because later they really, the standard deviation in particular, plays a big role as the course unfolds, starting in a couple chapters, as I said. Okay, so with that kind of behind us, we can see, the formulas for the variance and the standard deviation. Right, there's 4 different formulas there, and what's going on. There's some interesting symbols, and when you get formulas in statistics. They can be intimidating, and these are no exception, that's for sure. So let me go ahead and read the definition of variance. The average of the squared distances of each data value from the mean. Okay, and now let me just go ahead and read you the definition of standard deviation a little bit further down. The square root of the variance. Okay, so you could probably argue there's really only one formula here, because once we find the variance, to find the standard deviation, all we need to do is take the square root. Okay, now certainly the variance has significance in its own right, and you see variance used when statistics are spoken about, for different things. Occasionally you hear the variance was such and such. But as far as our class goes, really the standard deviation is between the two. It's really the standard deviation that we're after. And so in calculating the variance, that's really just a means to getting the standard deviation. And the variance is really going to be most of the work. Once we have the variance, well, it's simply a matter of taking the square root, and we'll have the standard deviation. Okay, so when we say the variance, we'll kind of go back to that. Take a look, and there's 2 formulas. There's one formula for a sample variance there at the beginning, and then below that you see the formula for the variance of a population. And they're very similar. Let's just talk about some of the elements of those formulas first. You see a couple of Greek letters in there. So for the standard deviation, or excuse me, for the variance of a population, it's denoted with this variable. So it kind of looks like an O with sort of a tail coming out the top. That is the Greek letter sigma. Okay, that's actually the lowercase version. All right, and there's a reason why they pick that particular Greek letter. I'll explain that in a little bit. We also see the uppercase sigma, which seems kind of confusing. That's part of both formulas. It's a coincidence that it ends up being sigma for both. It turns out we want the Greek letter S in both cases for a good reason. So we're not just trying to make things extra hard. This is the uppercase sigma, and it's going to stand for a summation, like you're taking a sum of things. Okay, so here are those formulas. Let me just show you all of these. Okay, so the first 2 formulas are for the sample variance and the population variance. Let's just take a look at these a little bit closer. Okay, so we call the sample variance S squared, so that later we can call the sample standard deviation S. Remember, once we have this, it's just a square root to get that. Similarly, for the population variance, we call that sigma squared. So once we have the value for sigma squared, to get the standard deviation, we'll take the square root and it's just sigma. Okay, really, again, like even the notation for s squared and sigma squared, lends itself to, it's really the standard deviation that we're after. I want to know S, the sample standard deviation, or I want to know sigma, the population standard deviation. So because the variance, is the square, and it really doesn't have all that much meaning in its own right, certainly not in our course, we're just going to call it S squared and sigma squared, because it's really the S and the sigma that we're after. And now here maybe it makes sense why we're using S and then the sigma, especially because it stands for standard deviation. S for standard deviation, sigma for standard deviation, just the Greek letter S. Okay. And then the uppercase sigma, well, because that stands for summation, which starts with an S as well. Now, what's going on amongst these formulas? What other things? Okay, well, let's take a look at the sample variance first. You'll notice it has an X bar. You may remember that to be the sample mean. Okay, sample variance uses the sample mean. The equivalent position in the population variance has mu. Well, that's the population mean. Okay, so the mean of the sample, the mean of the population makes sense. Okay, the capital X is kind of confusing, so let me explain that. The capital X will represent each data value one at a time. More on that when we do an example. Each data value done separately, kind of thing. Okay, and then we end up adding all of those values from each different data value plugged in. Okay, we'll do an example. I know that's probably not a good explanation just yet. We have the same idea happening in the population variance with the capital X and then the capital sigma there. And then N, and really this is the big difference between the two formulas, N minus 1 versus N. N is the sample size. How many data points do you have? Or it could be your population size. Sample size or population size. How many data values are there? Okay. Well, let's get to it. Let's take a look at practice number 9. And we're going to calculate some of these things. Okay. So let me go ahead and read it. It says in practice number 9, it says below is the amount of European auto sales in 6 particular years. The data are in millions of dollars. So as we read those numbers, 6 different years, European auto sales, I don't really know. Maybe this is one car company, one European car company. I'm not really sure. Whatever it is, that's our data. Okay. Adjusting my camera here a little bit. All right. So we see 11.2 million in 1 year, 11.9 million, 12.0, 12.8, 13.4, 14.3. Looks like sales are going up. If that's chronological anyway. Okay. That's all great. In part A, what are we trying to do? Calculate the population variance and population standard deviation. And we will round each to 3 decimal places. All right. So we're going to begin with the population. Oh, it's off the screen. The population variance and population standard deviation for this one. Okay. Let's take a look. Okay, so we see those formulas. Maybe I should just kind of keep that on the screen. All right. So let's try and identify the different parts. And let's begin. The simplest one is N. How many data points are there here in this example? Well, there's 1, 2, 3, 4, 5, 6. There are 6 different data points. So our N is 6. We're thinking of that as our population size. Okay. What else? Let's calculate mu, the population mean. So to calculate mu here, we're going to add our 6 numbers, and we're going to divide that by 6. So we've got 11.2 plus 11.9 plus 12.0 plus 12.8 plus 13.4 plus 14.3, all of that over 6. And this one actually turns out fairly well. It's 12.6. Okay, fantastic. So now we're going to take a look. We're going to do the numerator for our formula. We know that n is 6. We just figured out mu is 12.6. How can we get the rest of this? All right. Here's where the big X comes in and the uppercase sigma. All right. We're going to do these together, and I'm just going to show you. Maybe I'll just show you this part. So one at a time, we're going to go through each data value and plug that in for the capital X in that formula. So we're looking at capital X minus mu quantity squared. So we know the mu is 12.6. So we're going to begin by taking the first data value and plugging it in for the capital X, which is 11.2. So we'll take 11.2 minus 12.6, and we're going to square that. If you remember, the definition of the variance is has to do with the squares from the distance of the squares from the mean. Okay, so we take the distance to the mean and we square it. I'm going to grab my calculator and just do that along at the same time. So I subtract those and I square. And here I got 1.96. Okay, and then I'll go to the next one. And now I keep mu the same, but I go to the next data value. So now it's 11.9, so I plug that in. 11.9 minus 12.6, and I square that. And I got, for this one, 0.49. And we're just going to keep going until we've done them all. This is 0.36. We're halfway there. 12.8 minus 12.6. You notice the closer the value is to that mean, the smaller this result. Okay. And we'll do 13.4. Get that answer, then square it. Now this is starting to get a bit further away, so our answer is a little bit bigger. That first one was quite far away, so that was a large. Okay, well, anyway, we just got one left. 14.3 minus 12.6, and we're going to square. Oh, this one, that one will do it for us. Okay, that's the big one. 2.89. So we plugged in each. Had a breeze just kind of come by here. Okay, afternoon breeze. Probably hear my wind chime in the background as well. All right, we just plugged in each of our 6 data values separately, did that. And now, if we look back to our formula, we did each of these, and now the big sigma is telling us to sum them up, or to add them, you might say. So once we have all of those, the big sigma says, okay, take all those and add them together. And I did this earlier, but let me just go ahead and confirm that. 1.96 plus 0.49 plus 0.36 plus 0.04 plus 0.64 plus 2.89, 6.38. Yeah, that's it. Okay, so this number right here is our numerator in that formula. And then, of course, we know we're going to divide by the 6. So I need to continue on the next page. Here's what we got. We know sigma squared will equal 6.38 divided by 6. So let's go ahead and divide there. And the question told us to round to 3 decimal places. So there you go. When you round, 1.063. The next digit would be a 3, so we'll just keep it rounded that way. That's the population variance. Okay, in the same question it said to also find the population standard deviation. Well, that's really what we're after at the end of the day. Well, all we got to do at this point is take a square root, and we're going to round this to 3 decimal places as well. The square root of 1.063 is 1.031 when it's rounded. And that's our population standard deviation. Okay. Now maybe just a couple words. Now that we've done an example, let me just say a couple of words about what these numbers even mean. Like, how are they significant? And it's really not clear at this point. Like, what does population standard deviation even tell us? Okay, so we're still talking about the spread of the data, right? We're still in the section of our lecture measuring the spread. Variance and standard deviation measure the spread of the data. And so all I'm going to say at this point is that the higher the standard deviation, the more spread out your data is. The lower this number gets, the more tightly compacted that data is. So a standard deviation of 1.031 is actually pretty small. And you look at that data there, all of the numbers are between 11.2 and 14.3, right? The range is just a little bit over 3. I mean, this data is pretty well centralized, around 12 and a half or so. It'd be kind of right there in the middle. So pretty evenly spread and fairly close together. As this number gets bigger, then the more spread out those numbers are. And then the variance would follow along. So the bigger this number is, well, also the bigger, the more spread out they are. Okay, if you would like more of an explanation of variance and standard deviation, well, that'll come a little bit later in the course. Also, if you're just wondering, why are these formulas the way that they are? Okay, I understand that maybe they describe the spread, and I can accept that. But why would we calculate them the way that we have? Why would it be that we take each data value and subtract the mean and square it, then add those together? There's a really, really good explanation on a website, and they do, it's just kind of this story almost they put together to explain it. And they do it with these cartoon, they like take the heights of these dogs, like these cartoon dogs. They do a fantastic job of keeping it really, really simple of why the formula for population standard deviation is what it is, and then even the sample standard deviation. Okay, so I'm going to put a link to that website, right by our videos. If you want to check it out, you don't have to check it out, but if you're curious, I think they do a really good job. Okay, let's tackle part B. How do these values change if the data is thought of as a sample? So now we're going to do the sample variance and sample standard deviation, although we've actually done a lot of the work for those already because the formulas are so similar. Okay, let's take a look at sample variance, and I just went ahead and copied that formula over again for us, like so. Now, a lot of this work we've done already. Again, n is 6. Now, this time, we're not thinking of that data as an entire population. We're thinking of it as just a sample of a larger population. And that probably makes more sense here. Actually, well, let's think. If it's a sample, it's like, well, this is a sample of 6 years for this particular car company. If it was a population, well, that would make sense if the car company's only been around for 6 years. And this is all of the data that they have. But I'd say more than likely, this is a sample, not a population, just for the particular context here. All right, so anyway, how would that change anything? Well, now when we do the mean, it's not mu. We need to refer to it as x bar because it's a sample mean, but it would still be 12.6. Now, we can go straight to this. When we calculate that numerator, sigma capital X minus x bar quantity squared, all of those numbers would be the same numbers that we used previously. Now it's x bar, but where before it was mu, but it's still 12.6 and it's all of our same data values. Okay, so we'd still get 6.38 as our numerator here after doing those calculations. The difference between this formula and the population variance is now we divide by n minus 1. We're not going to divide by 6. We're going to divide by 5. 1 less than the sample size, which would give us a result I'll just show you all this, would give us an s squared when we round of 1.276 for the sample variance. And I apologize for the shadows here. Sample standard deviation, well, again, we take the square root, 1.130 when you round it. There's your sample standard deviation, which of course we just call s, lowercase. Now what's going on here? Okay, compare these numbers to the equivalent numbers we got for the population. So let's see, maybe let's just look at the standard deviation, 1.130. Before we got 1.031. A lot of ones and zeros and threes, kind of a side note. But what happened? Did this number get bigger or smaller when we did the sample? It got a little bit bigger, right? It went from 1.031 to 1.130. So it got bigger by about 0.1. Same with the sample variance. It got a little bit bigger. Before it was 1.063. Now it's 1.276. So that got bigger by about 0.2. Why is that? Well, we divided by a smaller number, so the result was a little bit bigger. Maybe that's one way to explain it. But probably a better way to explain it would be to say, why is it that we're subtracting 1 from the sample size? It seems like we should just divide by how many numbers there are. I mean, that's what you do when you take an average. Exactly, and that's exactly why for a sample we should do 1 less. When you're looking at a sample, you recognize that you don't have all of the information. We just have a piece, and maybe a small piece, of all of the information. So there's less confidence in your computations. And if there's less confidence, then you can't be as confident in how spread out the data is, right? So these numbers tell us how spread out those values are for just those 6 numbers. But if we're thinking of it as a sample, we realize, okay, there are other numbers that have not been taken into consideration. So we know whatever we would get for these, actually it's a little bit, there's a little bit more give to those. We have to allow for more error. And we can accomplish that by just subtracting 1 from the sample size. That makes the result a little bit bigger than it would have been for both those values. You kind of think, well, that's kind of a strange way to do it. Well, I agree, but that's what everyone has agreed to do for the last several hundred years when it comes to a sample. Because there's that little bit of unknown, they agreed, let's just subtract 1 from the sample size, and that makes these a little bit bigger than they would have been, to kind of take into consideration that there's more data out there that's unknown. I have summarized this. If you want to write it down or not, just put it down in words here. Why divide by n-1 in the sample? Since we know we don't have all of the information, this is a way to account for unknown values that might be further from the mean. We can't say with absolute confidence how spread out or unspread out the data is. So we give a little bit, making our values a little bit bigger to account for that. Okay. Let's go ahead and stop this video here. That was a long example.